Oversampling and undersampling are the techniques to change the ratio of the classes in an imbalanced modeling dataset. This step-by-step tutorial explains how to use oversampling and undersampling in Python to adjust the imbalanced classes for machine learning models. We will compare four methods with the baseline random forest model results. They are random oversampling, synthetic minority oversampling technique, which is usually called SMOT, random undersampling, and near-miss undersampling. Hi everyone. This is Amy from Grab and Go Info. I publish step-by-step machine learning tutorials every week. If you are interested in data science, machine learning, deep learning, and natural language processing, please subscribe to my channel and get notified when I publish new contents. Let's get started. First off, what is the imbalance classification? Imbalance classification is also called rare event modeling. When the target label for a classification modeling dataset is highly imbalanced, we call the minority event to be a rare event. In this case, the model tends to get learnings from the majority class, and predicting the minority class can be challenging. For example, if only 0.01% of the dataset is the minority event, the model tends not to do a good job identifying the pattern of the minority event. Rare event modeling for imbalanced datasets has many use cases. Fraud event detection, severe disease diagnosis, and credit card invitation response are some examples. First, let's import the libraries for this tutorial. We will use a Python library called Imbalanced Learn to handle imbalanced datasets, so let's install the library first. Note that the version of the package may be different from mine, depending on when you run the installation. Now let's import the Python libraries. We need to import make classification from sklearn to create the modeling dataset. Import pandas and numpy for data processing, matplotlib and seaborn for visualization. We also need the train test split, random forest classifier, and classification report for model training and performance evaluation. For the oversampling and undersampling, we need to import random oversampler, SMOT, random undersampler, and near-miss counter will help us count the number of records after oversampling and undersampling. Using make classification from the sklearn library, we create an imbalanced dataset with two classes. The minority class is 0.5% of the dataset. I made two features to predict which type each data point belongs to. The dataset gives us around 1% data points for the minority class. It is higher than the specified weights of 0.5%, but works for demonstrating the rare event modeling process. Let's visualize the data using a scatter plot. We can see that the majority of the dataset belongs to class 0, and a small portion of the dataset belongs to class 1. The next step is to do a train test split for the imbalanced data. In this step, we split the dataset into 80% training and 20% validation. Random state ensures that we have the same train test split every time. The seed number for random state does not have to be 42, and it can be any number. The train test split gives us 80,000 records for the training dataset and 20,000 for the validation dataset. Thus, we have 79,183 data points from the majority class and 817 from the minority class in the training dataset. Before building the model, we need to decide the performance metric we would like to optimize towards. The most critical performance metric for the rare events modeling is usually the minority class recall or precision values. For example, in the context of fraud detection, we would like to maximize the true positive rate and capture as many fraud cases as possible. So recall for the minority class is the metric we would like to optimize. While in the context of spam email classification, we would like to minimize the false positive rate and not misclassify any important email as spam. So the precision for the minority class is the metric we would like to optimize. In this tutorial, we use fraud detection as an example and choose recall for the minority class as the metric to optimize. We first check the model performance using the imbalanced data directly. A model without oversampling or undersampling gives us a baseline to compare the model performance. A random forest model is used as an example here. After training the model using the training dataset and make predictions on the testing dataset, we got the model performance results. The recall value ranges from 0 to 1. 0 represents 0% true positive rate, and 1 represents 100% true positive rate. The output shows that the minority class has a recall of 0.03, which means around 3% of the minority class is captured by the model. One way of oversampling is to generate new samples for the minority class by sampling with replacement. The random oversampler from the Imbalanced Learn library provides such functionality. Note that we apply the oversampling technique to the training dataset only. The testing dataset needs to keep untouched. After random oversampling, the minority category increased from 817 to 79,183. The same as the majority category. From the visualization, we can see more orange minority data points after random oversampling. Now let's run the same random forest model and check the performance after random oversampling. We can see that random oversampling did not provide a better result. We get the same recall and the similar F1 score, and the precision decreased. Thus, the random oversampling has worse performance than the baseline model with no class ratio adjustment. Let's try SMOTE and see how it works. Instead of randomly oversampling with replacement, SMOTE takes each minority sample and introduces synthetic data points, connecting the minority sample and its nearest neighbors. Neighbors from the k nearest neighbors are chosen randomly. Similar to random oversampling, the minority category increased from 817 to 79,183 after SMOTE oversampling. Comparing the graph between random oversampling and SMOTE, we can see that the synthetic data points created by SMOTE are all along a line. Now let's run the same random forest model on the SMOTE dataset and check its performance. We can see that the model using SMOTE increased recall from 0.03 to 0.24. Thus, it significantly improved the model's ability to capture the minority class. We have tried two oversampling techniques, random oversampling and SMOTE. Now let's try the undersampling techniques. Let's check out random undersampling first. Random undersampling randomly picks data points from the majority class. After the sampling, the majority class should have the same number of data points as the minority class. We set a random state for the random undersampler so we can reproduce the same samples, then run the fit resample on the training dataset. After random undersampling, the majority category decreased from 79,183 to 817, the same as the minority category. The visualization shows that we have fewer data points for the model. After randomly sampling, the recall increased to 0.50, and it's much better than the oversampling results. Let's try another undersampling method called near miss. Near miss from the Imbalanced Learn library uses the k nearest neighbors to do undersampling. There are 3 versions of near miss algorithms depending on how the sampling is implemented. In this tutorial, we are using version 3, which is a 2-step algorithm. First, for each data point in the minority class, k nearest neighbors are sampled. Then, for each majority data point that is sampled, we calculate the average distance to the n nearest neighbors. The data points with the largest average distance are sampled. The visualization shows the pattern of the near-miss undersampling. Near-miss gives us the recall value of 0.57, which is the highest among the 4 methods. In this tutorial, we talked about how to use oversampling and undersampling techniques in imbalanced classification models. You have learned what is imbalanced classification, how to decide the model performance metrics, how to do oversampling using random oversampling and SMOTE, how to do undersampling using random undersampling and near-miss, and how to compare the performance of oversampling and undersampling. We found that undersampling has better performance than oversampling. Within undersampling, near-miss algorithm has better performance than random undersampling. If you found the information in this tutorial helpful, please click the like button and subscribe to the channel. If you prefer the written version of the tutorial, please go to grabandgoinfo.com. I will put the link in the video description. This is the blog post for this video. It has all the code and explanations, as well as related article recommendations, such as balanced weight adjustment, isolation forest for anomaly detection, and use neural network model for imbalanced classification. Thank you for watching. See you in the next video.